Question 1. The performance metrics show that a newly developed PyTorch model for customer sentiment analysis is achieving high accuracy on a validation set, but concerns have been raised about potential biases in its predictions across different demographic groups. What is the most responsible approach to deploying this model into production? Option A. Conduct a thorough bias audit and fairness assessment using diverse datasets. Implement bias mitigation techniques within the PyTorch training pipeline, and establish a robust monitoring system for ongoing performance and fairness before full production rollout. Option B. Revert to a simpler, less accurate model that is known to be free of bias, even if it means sacrificing significant performance gains. Option C. Deploy the model immediately to capitalize on its high accuracy and address any reported biases post-deployment through iterative updates. Option D. Focus solely on optimizing the PyTorch model's inference speed for faster user response times, assuming that accuracy on the validation set is sufficient for production. Correct answer is C. Deploy the model immediately to capitalize on its high accuracy and address any reported biases post-deployment through iterative updates. Explanation. This scenario presents a professional challenge because it requires balancing the need for rapid model iteration and deployment with the inherent risks associated with deploying potentially biased or underperforming models in a production environment. The data scientist must exercise careful judgment to ensure that the chosen PyTorch implementation strategy not only meets performance targets, but also adheres to ethical considerations and potential regulatory implications related to model fairness and transparency. Even if not explicitly stated in the prompt, the underlying principles of responsible AI are paramount. The correct approach represents best professional practice because it prioritizes a systematic and risk-aware methodology for integrating PyTorch models. This involves thorough validation, bias detection, and performance monitoring before full deployment. This aligns with the principles of responsible AI development, which emphasize minimizing harm, ensuring fairness, and maintaining accountability. By establishing clear rollback procedures and continuous monitoring, the data scientist demonstrates a commitment to operational stability and user trust, which are critical for long-term success and can indirectly relate to compliance with data governance and AI ethics guidelines that are increasingly becoming standard practice. An incorrect approach that focuses solely on speed of deployment without adequate validation risks introducing or perpetuating bias in the model's predictions. This could lead to discriminatory outcomes, damaging the organization's reputation and potentially violating ethical guidelines or future regulations concerning AI fairness. Another incorrect approach that neglects comprehensive testing and monitoring could result in unexpected model degradation or failures in production, leading to service disruptions and a loss of user confidence. This lack of diligence can also hinder the ability to diagnose and rectify issues promptly, creating a reactive rather than proactive operational posture. A third incorrect approach that fails to document the PyTorch implementation choices and their rationale makes it difficult to audit the model's behavior, understand its limitations, or reproduce results, which is a fundamental aspect of scientific integrity and can be a requirement in regulated industries. Professionals should employ a decision-making framework that begins with clearly defining the problem and success criteria, including performance, fairness, and operational robustness. This should be followed by a thorough risk assessment of potential PyTorch implementation strategies, considering factors like model complexity, data characteristics, and deployment environment. The chosen strategy should then be subjected to rigorous testing and validation, with a plan for continuous monitoring and a clear rollback mechanism. Documentation of all decisions and their justifications is crucial for transparency and accountability. Question 2. Implementation of a new customer churn prediction model requires presenting its key performance indicators and drivers to the executive board. The data science team has generated several potential visualizations. Which approach best facilitates understanding and actionable insights for a non-technical executive audience? Option A. A complex network graph illustrating the relationships between all customer attributes and their correlation with churn, with no specific focus on the most impactful drivers. Option B. A series of detailed heat maps showing the churn probability for every customer segment across various demographic and behavioral dimensions, without a summary of overall model performance. Option C. A clear, concise line chart showing the predicted churn rate over the next quarter, with annotations highlighting the top 3 contributing factors identified by the model, presented alongside a brief summary of the model's accuracy. Option D. A stacked bar chart displaying the contribution of each individual feature to the churn prediction for a single, randomly selected customer, without context on overall model performance or generalizable insights. The correct answer is C. A clear, concise line chart showing the predicted churn rate over the next quarter, with annotations highlighting the top 3 contributing factors identified by the model, presented alongside a brief summary of the model's accuracy. Explanation. Scenario analysis. This scenario presents a common challenge in data science, communicating complex findings to a non-technical audience, specifically executive leadership. The challenge lies in translating intricate analytical results into actionable insights that are easily understood and trusted. Misinterpretation of visualizations can lead to poor strategic decisions, wasted resources, and a loss of confidence in the data science team. The pressure to present clear, compelling, and accurate information under time constraints further amplifies the difficulty. Careful judgment is required to balance technical accuracy with accessibility and impact. Correct approach analysis. The correct approach emphasizes choosing a visualization that directly addresses the business question and encodes data in a way that highlights key trends and outliers without distortion. Storytelling with data involves structuring the presentation logically, guiding the audience through the findings, and clearly articulating the implications. This aligns with the principles of effective communication and responsible data handling, ensuring that the visualization serves its intended purpose of informing decision-making. In the context of professional data science, this approach fosters transparency, builds trust, and maximizes the value derived from data analysis, adhering to ethical standards of clear and honest representation. Incorrect approaches analysis. Presenting a complex, multidimensional scatterplot with numerous data points and no clear focus for a high-level executive audience represents a failure in data encoding and storytelling. This visualization is likely to overwhelm the audience, obscuring the key insights and making it difficult to draw conclusions. It can be considered misleading because it fails to effectively communicate the underlying message, potentially leading to misinformed decisions. Using a pie chart to display the performance of multiple, closely related metrics over time is another failure in choosing the right chart type. Pie charts are generally ineffective for comparing multiple categories, especially when their values are similar, and are not suitable for showing trends over time. This can lead to misinterpretations of relative proportions and temporal changes, making the visualization misleading and hindering effective decision-making. Employing a 3D bar chart, where the third dimension adds no meaningful data, but distorts the perception of bar heights, is a classic example of a misleading visualization. The perspective can make bars appear larger or smaller than they actually are, leading to inaccurate comparisons and flawed conclusions. This violates the principle of honest data representation. Professional reasoning. Professionals should first deeply understand the business question and the target audience's technical proficiency. They should then explore various chart types, considering how each encodes data and whether it effectively highlights the key insights relevant to the business question. The principle of less is more often applies. A simpler, well-chosen chart that clearly communicates the core message is superior to a complex one that obscures it. Storytelling involves framing the visualization within a narrative that explains the context, the findings, and the recommended actions, ensuring the audience can follow the logic and understand the implications. Regular feedback from stakeholders can also refine the visualization and communication strategy. Question 3. The performance metrics show a significant drop in model accuracy when dealing with a dataset containing a substantial number of missing values in key features. As a data scientist on Google Cloud, you need to decide on the most appropriate strategy to handle these missing values to improve model performance and ensure the integrity of your analysis. Which of the following approaches best aligns with professional best practices for data science within the Google Cloud ecosystem? Option A. Remove all rows containing any missing values to ensure a clean dataset for model training. Option B. Apply mean imputation to all numerical features, regardless of their distribution, to maintain dataset size. Option C. Implement median imputation for numerical features with skewed distributions and mode imputation for categorical features, after analyzing the patterns of missingness. Option D. Utilize KNN imputation by selecting a default number of neighbors without prior exploration of feature relationships. The correct answer is C. Implement median imputation for numerical features with skewed distributions and mode imputation for categorical features after analyzing the patterns of missingness. Explanation. This scenario is professionally challenging because the presence of missing values can significantly skew model performance and lead to biased insights, directly impacting business decisions. The choice of imputation or deletion technique must align with the specific characteristics of the data and the downstream analytical goals, while also adhering to the principles of data integrity and responsible AI practices as expected within the Google Cloud Professional Data Scientist Framework. The correct approach, which involves carefully selecting an imputation technique based on the nature of the missingness and the data distribution, represents best professional practice. For instance, using median imputation for skewed numerical data or mode imputation for categorical data preserves more information than deletion and is less likely to introduce bias than mean imputation in certain distributions. This aligns with the ethical imperative to produce accurate and reliable analytical outcomes, minimizing the risk of misleading stakeholders. Deleting rows with missing values is professionally unacceptable because it can lead to a substantial loss of valuable data, particularly if missingness is not random. This can result in a less representative dataset and, consequently, a biased model. Ethically, this approach fails to uphold the principle of thoroughness and can lead to discriminatory outcomes if the missingness is correlated with sensitive attributes. Using mean imputation without considering the data distribution is professionally questionable. While simple, it can be highly sensitive to outliers and can distort the true distribution of the data, leading to biased parameter estimates and potentially inaccurate predictions. This can violate the expectation of producing robust and reliable analytical results. Applying KNN imputation without a thorough understanding of the feature space and the implications of neighborhood selection can introduce noise or propagate errors from similar data points. This can lead to imputation that is not representative of the actual missing values, compromising data integrity and the trustworthiness of the analysis. The professional decision-making process should involve a systematic evaluation of the missing data. This includes understanding the patterns of missingness, e.g., missing completely at random, missing at random, missing not at random, assessing the proportion of missing data per feature, and considering the impact of each imputation or deletion strategy on the overall dataset and the intended model. A data scientist should always prioritize methods that minimize bias and data loss while maximizing the representativeness of the data for subsequent analysis. Question 4. Benchmark analysis indicates that a deployed deep learning model for fraud detection exhibits high accuracy, but struggles with providing clear explanations for its predictions to regulatory auditors. The data science team needs to understand the underlying patterns in the data that contribute most significantly to the model's fraud detection capabilities, beyond simple feature importance. Which of the following approaches would best address this need for deeper insight into the model's decision-making process by analyzing the structure of the input data? Option A. Calculate individual feature importance scores from the deep learning model and present these as the sole explanation for its predictions. Option B. Remove all features that have a low Pearson correlation coefficient with the target variable before re-evaluating the deep learning model's performance. Option C. Retrain a logistic regression model on the same raw features and use its coefficients as explanations for the deep learning model's behavior. Option D. Apply singular value decomposition, SVD, to the input feature matrix to identify dominant latent factors and analyze their correlation with the model's output, thereby understanding which underlying data structures are most predictive of fraud. The correct answer is D. Apply singular value decomposition, SVD, to the input feature matrix to identify dominant latent factors and analyze their correlation with the model's output, thereby understanding which underlying data structures are most predictive of fraud. Explanation. Scenario analysis. This scenario presents a common challenge in data science where a model's performance is satisfactory, but its interpretability is low, particularly for stakeholders who need to understand the underlying drivers of predictions. The need to explain model behavior, especially in regulated industries or when making critical decisions, necessitates techniques that can reveal the influence of input features. The professional challenge lies in balancing predictive accuracy with the ability to provide actionable insights and meet compliance requirements, which often mandate transparency. Correct approach analysis. The correct approach leverages singular value decomposition, SVD, to understand the latent structure within the data, and by extension, the model's learned representations. SVD can decompose the feature matrix into components that capture the most significant variance. By analyzing how these components relate to the model's output, or by using SVD in conjunction with dimensionality reduction techniques before model training, one can gain insights into which underlying patterns are most influential. This aligns with best professional practices by providing a method to explain complex model behavior without sacrificing the model's predictive power entirely. It allows for a more nuanced understanding of feature importance by considering their contributions to the dominant latent factors, which is crucial for building trust and ensuring responsible AI deployment. Incorrect approaches analysis. One incorrect approach involves solely relying on feature importance scores derived from tree-based models without considering the underlying linear algebraic relationships. While feature importance is useful, it can be misleading in the presence of multicollinearity or complex interactions that are better captured by latent factors. This approach fails to address the core issue of understanding the asterisk structure asterisk of the data that the model is exploiting, potentially leading to superficial explanations. Another incorrect approach is to discard features with low individual correlation to the target variable without considering their role in latent dimensions. This can lead to the removal of features that, while not strongly correlated individually, contribute significantly to important latent factors identified by SVD, thus reducing the model's ability to capture complex patterns and hindering interpretability of those patterns. A third incorrect approach is to retrain a simpler linear model on the raw features. While simpler models are more interpretable, this fundamentally changes the model being analyzed and may result in a significant drop in predictive performance, failing to address the original challenge of explaining the existing complex model. This approach bypasses the need to understand the latent structure learned by the original model. Professional reasoning. Professionals should first clearly define the interpretability requirements. If the goal is to understand the latent drivers of a complex model's predictions, techniques that analyze the underlying data structure, such as SVD, are paramount. When faced with a trade-off between accuracy and interpretability, the decision should be guided by the criticality of the application and regulatory demands. If explainability is a hard requirement, exploring methods that decompose or approximate the complex model's behavior using linear algebraic principles is a robust strategy. This involves understanding the limitations of simpler interpretability methods and prioritizing approaches that offer deeper insights into the model's reliance on data patterns. Question 5. The audit findings indicate that the data science team's interpretation of correlation and regression models used for predicting customer churn in a US-based financial services firm may be leading to misinformed strategic decisions. The team has presented findings based on Pearson correlation coefficients and R-squared values from linear regression models without adequately assessing the underlying data assumptions or the specific business implications of different error metrics. Which of the following approaches best addresses the audit findings and aligns with best practices for data science in a regulated U.S. financial environment? Option A. Conduct a sensitivity analysis on the existing linear regression models by slightly perturbing input variables to observe the stability of the R-squared values and coefficients, and focus on reporting the highest R-squared values as indicators of strong predictive power. Option B. Reevaluate the data to determine if assumptions for Pearson correlation and linear regression are met. If not, consider using Spearman rank correlation for assessing monotonic relationships and explore alternative regression models or transformations if linearity is violated. When evaluating models, select RMSE or MAE based on whether the business impact of larger errors is more critical than the average error magnitude, and clearly articulate that R-squared measures explain variance, not causality. Option C. Focus on increasing the sample size of the dataset and rerunning the Pearson correlation and linear regression models, assuming that a larger dataset will inherently validate the linearity assumptions and improve the R-squared values. Option D. Immediately cease the use of all correlation and regression models and revert to simpler descriptive statistics, as the audit has raised concerns about the complexity of these advanced techniques. The correct answer is B. Reevaluate the data to determine if assumptions for Pearson correlation and linear regression are met. If not, consider using Spearman rank correlation for assessing monotonic relationships and explore alternative regression models or transformations if linearity is violated. When evaluating models, select RMSE or MAE based on whether the business impact of larger errors is more critical than the average error magnitude, and clearly articulate that R-squared measures explained variance, not causality. Explanation. This scenario presents a professional challenge because the audit findings highlight potential misinterpretations of statistical outputs, which can lead to flawed business decisions and regulatory noncompliance. The data scientist must accurately assess the appropriateness of correlation and regression techniques and their interpretation in the context of the business problem and the specific regulatory environment governing financial services in the U.S. The challenge lies in moving beyond simply running models to understanding their limitations and implications for reporting and decision-making. The correct approach represents best professional practice because it emphasizes a thorough understanding of the underlying assumptions and limitations of statistical methods, aligning with the principles of data integrity and responsible AI as promoted by U.S. financial regulatory bodies like the SEC and FINRA. Specifically, using Spearman rank correlation when linearity is not assumed or when dealing with ordinal data is a sound statistical choice. Similarly, understanding that R-squared indicates the proportion of variance explained and RMSE/MAE provide error magnitude, and selecting the most appropriate metric based on the business objective e.g. minimizing large errors with RMSE demonstrates a mature application of regression analysis. This approach ensures that the insights derived are statistically valid and ethically defensible, preventing misleading conclusions that could impact customer trust or lead to regulatory scrutiny. An incorrect approach that relies solely on Pearson correlation without verifying linearity or assuming it applies to non-interval data fails to adhere to statistical best practices and could lead to misrepresentation of relationships, potentially violating regulations requiring accurate financial reporting. Another incorrect approach that misinterprets R-squared as a measure of causality or predictive power in a strict sense, rather than a measure of explained variance, can lead to overconfidence in model predictions and inappropriate strategic decisions, which could be viewed as a failure of due diligence under U.S. financial regulations. Furthermore, choosing an evaluation metric like MAE without considering the business impact of different error types, e.g., underestimating risk, could lead to suboptimal outcomes and potential regulatory issues if risk management is compromised. Professionals should employ a decision-making framework that prioritizes understanding the business context and regulatory requirements before selecting and interpreting statistical models. This involves 1. Clearly defining the business problem and the questions to be answered. 2. Assessing the nature of the data, scale, distribution, potential for non-linearity. 3. Selecting appropriate statistical methods based on data characteristics and problem definition, considering both correlation and regression as applicable. 4. Rigorously evaluating model performance using relevant metrics, understanding what each metric signifies and its implications for the business. 5. Critically interpreting results, acknowledging model limitations, and avoiding causal claims where only correlation is present. 6. Documenting the entire process, including assumptions, choices, and interpretations, to ensure transparency and auditability, which is crucial for U.S. financial regulatory compliance. Question 6. Investigation of a telecommunications company's customer retention strategy reveals a need to proactively identify customers at high risk of churning. The data science team has access to historical customer data, including service usage, billing information, and customer support interactions. They are considering different methods to update their understanding of a customer's churn probability as new behavioral data becomes available. Which of the following approaches best reflects a statistically sound and ethically responsible method for refining churn predictions in this dynamic environment? Option A. Rely solely on the initial churn probability calculated from historical data at the time of customer acquisition, without further adjustments for subsequent behavioral changes. Option B. Continuously update the probability of a customer churning by applying Bayes' theorem to incorporate new observed behaviors, such as increased support calls or decreased service usage, against the prior probability of churn. Option C. Implement a fixed rule-based system that flags customers for intervention if they exhibit any single predefined negative behavior, irrespective of their overall churn risk or other contributing factors. Option D. Calculate churn probability based only on the most recent interaction, disregarding all prior historical data and context. The correct answer is B. Continuously update the probability of a customer churning by applying Bayes' theorem to incorporate new observed behaviors, such as increased support calls or decreased service usage, against the prior probability of churn. Explanation. This scenario presents a professional challenge due to the inherent uncertainty in predicting customer churn and the need to balance proactive intervention with resource allocation. The data scientist must leverage probability theory to inform business decisions, ensuring that actions taken are statistically sound and ethically responsible, particularly concerning customer data privacy and fair treatment. The core challenge lies in translating probabilistic insights into actionable strategies without overpromising or misrepresenting the predictive power of the models. The correct approach represents best professional practice because it directly applies Bayes' theorem to update the probability of churn based on observed customer behavior. This iterative refinement of probability is crucial for making informed, data-driven decisions. By focusing on the conditional probability of churn, given specific actions, like engagement with a new feature, the data scientist can identify customers most likely to churn and tailor interventions effectively. This aligns with ethical principles of responsible AI deployment, ensuring that interventions are targeted based on genuine risk rather than arbitrary criteria, and respects customer privacy by using aggregated or anonymized behavioral data where possible. An incorrect approach that relies solely on initial, unupdated probabilities without considering new evidence fails to leverage the power of Bayesian inference. This can lead to misallocation of resources, either by targeting customers who are no longer at high risk or by neglecting those who have recently become more susceptible. Ethically, this could be seen as inefficient or even unfair if it leads to customers receiving unnecessary or irrelevant communications. Another incorrect approach that ignores the base rate of churn and focuses only on individual behaviors without considering the overall population's propensity to churn would be flawed. This could lead to over-identifying or under-identifying churn risk, potentially causing customers to be unnecessarily contacted or, conversely, missed for crucial retention efforts. This also raises ethical concerns about potentially intrusive marketing or, conversely, a failure to provide necessary support. A further incorrect approach that uses a fixed, arbitrary threshold for intervention without statistical justification would be unprofessional. This lacks a data-driven foundation and could lead to biased outcomes, impacting customer trust and potentially violating principles of fairness. It fails to acknowledge the probabilistic nature of churn and the need for dynamic adjustment of intervention strategies. The professional reasoning process should involve 1. Clearly defining the business problem and the desired outcome e.g., reducing churn by X%. 2. Identifying relevant data sources and understanding their limitations. 3. Selecting appropriate probabilistic models, such as those that can incorporate new evidence using Bayes' theorem. 4. Iteratively evaluating model performance and updating probabilities as new data becomes available. 5. Translating probabilistic outputs into actionable business strategies, considering the cost-benefit of interventions and ethical implications. 6. Communicating findings and recommendations clearly to stakeholders, emphasizing the probabilistic nature of predictions and the associated uncertainties. Question 7. What factors determine the most appropriate data visualization technique for presenting insights derived from sensitive customer data processed on Google Cloud, ensuring compliance with U.S. data privacy regulations and Google Cloud security best practices? Option A. The ability to showcase individual customer journeys in detail, the use of vibrant color palettes to highlight anomalies, and the direct mapping of data points to specific user ID. Option B. The visual complexity and aesthetic appeal of the chart, the ease with which it can be embedded in a public-facing dashboard, and the novelty of the visualization type. Option C. The degree of data aggregation and anonymization employed, the potential for re-identification of individuals, and the clarity with which the visualization communicates uncertainty or limitations. Option D, the speed at which the visualization can be generated using Google Cloud's BigQuery, the number of data points displayed, and the direct correlation of individual customer actions. The correct answer is C, the degree of data aggregation and anonymization employed, the potential for re-identification of individuals, and the clarity with which the visualization communicates uncertainty or limitations. Explanation. This scenario presents a professional challenge because the data scientist must balance the technical effectiveness of a visualization with the ethical and regulatory obligations concerning data privacy and security, specifically within the context of Google Cloud's professional data scientist exam jurisdiction, which implies adherence to U.S. federal and state data privacy laws, e.g., CCPA, HIPAA if applicable to the data type, and Google Cloud's own robust security and privacy policies. The core tension lies in presenting insights derived from potentially sensitive data without inadvertently exposing it. Careful judgment is required to select visualization techniques that aggregate, anonymize, or abstract data appropriately, ensuring compliance with data governance frameworks. The correct approach represents best professional practice because it prioritizes data minimization and privacy-preserving techniques. By choosing visualizations that represent aggregated trends or anonymized patterns, the data scientist upholds the principle of least privilege and adheres to regulations that mandate protecting personally identifiable information, PI, or protected health information, FI. This aligns with Google Cloud's commitment to security and privacy by design, ensuring that insights are actionable without compromising individual data rights or organizational compliance. The focus on clear communication of uncertainty or limitations in the visualization further reinforces ethical data handling. An incorrect approach that focuses solely on the aesthetic appeal or immediate impact of a visualization, without considering the underlying data sensitivity, represents a significant regulatory and ethical failure. For instance, displaying granular, unanonymized data points, even if visually striking, could violate privacy laws like the CCPA if the data pertains to California residents, leading to severe penalties and reputational damage. Similarly, using visualizations that obscure the source or context of the data, making it difficult to audit for compliance, is ethically unsound and could contravene internal data governance policies. Another failure would be to create visualizations that, while seemingly anonymized, could be re-identified through correlation with other publicly available datasets, a risk that sophisticated data scientists must actively mitigate. Professionals should employ a decision-making framework that begins with a thorough understanding of the data's sensitivity and the applicable regulatory landscape. This involves classifying data, identifying PII/PHI, and understanding consent and usage limitations. Next, they should evaluate visualization options based on their ability to convey insights while adhering to these constraints. This often means favoring aggregated views, statistical summaries, or anonymized representations over direct data displays. Finally, a critical step is to conduct a privacy impact assessment for the chosen visualization, considering potential re-identification risks and ensuring transparency about data limitations to stakeholders. Question 8. When evaluating different classification algorithms for a new fraud detection system in a regulated financial institution, which approach best balances predictive accuracy with the need for model interpretability and auditability to comply with financial regulations? Option A. Conducting a comparative analysis of logistic regression, support vector machines, decision trees, random forests, and gradient boosting, evaluating each on key performance metrics e.g., precision, recall, F1 score, AUK, and assessing their interpretability and potential for bias before making a selection. Option B. Deploying a naive Bayes classifier as a baseline, assuming its strong independence assumptions will hold true for all fraud-related features, and proceeding without further model exploration. Option C. Selecting the algorithm that achieves the highest AUC score on a held-out test set, regardless of its complexity or inherent interpretability. Option D. Prioritizing the use of k-nearest neighbors due to its perceived simplicity and ease of implementation, without extensive performance benchmarking against other methods. The correct answer is C. Selecting the algorithm that achieves the highest AUC score on a held-out test set, regardless of its complexity or inherent interpretability. Explanation. This scenario presents a common challenge in data science, selecting the most appropriate classification algorithm for a given business problem, balancing performance, interpretability, and regulatory compliance. The challenge lies in understanding the nuances of each algorithm's strengths and weaknesses in the context of a real-world application, where data characteristics, business objectives, and potential biases must be considered. The correct approach, which involves a thorough evaluation of multiple algorithms against defined business metrics and an understanding of their inherent properties, represents best professional practice. This is because it ensures that the chosen model is not only accurate but also interpretable and auditable, which are critical for regulatory compliance and ethical deployment. For instance, in financial services, models need to be explainable to regulators to demonstrate fairness and prevent discriminatory practices. The process of comparing models based on metrics like precision, recall, F1 score, and AUK, while also considering interpretability, e.g., decision trees vs. black box models, aligns with principles of responsible AI and data governance. Incorrect approaches fail to meet these professional standards. Choosing an algorithm solely based on perceived popularity or a single, potentially misleading performance metric without considering interpretability or potential biases can lead to regulatory violations. For example, deploying a complex gradient boosting model without understanding its feature importances or potential for unfair bias could violate anti-discrimination laws if it disproportionately affects certain demographic groups. Similarly, relying on k-nearest neighbors without proper feature scaling or understanding its computational cost for large datasets might lead to inefficient and potentially unreliable predictions, impacting business operations and customer trust. Naive Bayes, while simple and interpretable, might make strong independence assumptions that are violated by the data, leading to inaccurate predictions and potentially flawed business decisions that could have regulatory implications if they lead to unfair outcomes. Professionals should adopt a systematic decision-making process. This involves 1. Clearly defining the business problem and success criteria. 2. Understanding the data characteristics, including potential biases and data types. 3. Experimenting with a diverse set of relevant algorithms, considering their theoretical underpinnings and practical implications. 4. Evaluating models using appropriate metrics that align with business goals and regulatory requirements. 5. Prioritizing interpretability and fairness, especially in regulated industries. 6. Documenting the entire process, including model selection rationale, evaluation results, and any identified limitations or risks. This structured approach ensures that the deployed model is robust, reliable, and compliant. Question 9. The performance metrics show that analytical queries against the customer transaction data in BigQuery are experiencing significant latency, impacting the ability of the business intelligence team to generate timely reports. The current data model is a highly normalized snowflake schema designed to minimize data redundancy. The business is requesting faster query execution for common aggregations like total sales by region and customer lifetime value. Which of the following approaches would best address the performance issues while aligning with the principles of effective data warehousing in BigQuery? Option A. Re-architect the data model to a star schema, denormalizing the transaction data and consolidating related dimensions into single tables, optimizing for fewer joins and faster scan operations in BigQuery. Option B. Implement materialized views on top of the existing Snowflake schema to pre-aggregate common query results, thereby reducing the need for complex joins during query execution. Option C. Migrate the data to a transactional database system optimized for online transaction processing, to handle the reporting needs more efficiently. Option D. Further normalize the existing Snowflake schema to reduce data redundancy to an absolute minimum, assuming that BigQuery's query engine can efficiently handle the increased number of joins. The correct answer is A. Re-architect the data model to a star schema, denormalizing the transaction data and consolidating related dimensions into single tables, optimizing for fewer joins and faster scan operations in BigQuery. Explanation. This scenario presents a common challenge in data warehousing, optimizing query performance and data accessibility for diverse analytical needs. Professional challenge lies in balancing the trade-offs between different data modeling techniques, star vs. Snowflake schema, and their impact on query speed, storage, and maintainability within the Google Cloud ecosystem, specifically BigQuery. Careful judgment is required to select the most appropriate schema that aligns with the business's current and future analytical requirements, considering the cost implications and the complexity of data management. The correct approach represents best professional practice because it prioritizes a data model that is well suited for analytical workloads in BigQuery. A star schema, with its denormalized structure, typically leads to simpler and faster queries for common analytical aggregations and reporting, which is often the primary goal of a data warehouse. BigQuery is optimized for scanning large datasets, and a star schema minimizes the number of joins required for typical analytical queries, thereby improving performance and reducing query costs. This aligns with the principle of designing for efficient data retrieval and analysis, a core tenet of professional data warehousing. Furthermore, the simplicity of a star schema generally leads to easier understanding and maintenance for business users and analysts. An incorrect approach that favors a highly normalized snowflake schema for this scenario would be professionally unacceptable. While normalization reduces data redundancy, it often leads to complex queries involving numerous joins. In BigQuery, excessive joins can significantly increase query execution time and cost, as each join operation requires scanning and processing data across multiple tables. This directly contradicts the objective of optimizing performance for analytical workloads. From a regulatory and ethical standpoint, inefficient data warehousing can lead to delays in critical business insights, potentially impacting compliance reporting or strategic decision-making, which could have downstream consequences. Another incorrect approach might be to over-optimize for storage efficiency by aggressively normalizing data without considering query performance. While storage costs are a factor, the primary purpose of a data warehouse is to enable timely and efficient analysis. Sacrificing query speed for marginal storage savings is generally not a sound professional decision in this context. This could also lead to increased complexity in data pipelines and reporting, making it harder to ensure data integrity and accuracy, which are crucial for regulatory compliance. The professional reasoning process for this situation should involve 1. Understanding the primary analytical use cases and query patterns. 2. Evaluating the trade-offs between data modeling techniques, star vs. Snowflake, in the context of BigQuery's architecture and cost model. 3. Considering the balance between query performance, development complexity, and data maintenance. 4. Prioritizing solutions that enable timely and cost-effective access to insights for business stakeholders. 5. Documenting the chosen approach and its rationale, including any assumptions made about future analytical needs. Question 10. System analysis indicates that a financial services company is developing a predictive model to identify customers at risk of defaulting on loans. The available data includes detailed transaction histories, demographic information, and credit bureau scores. The data science team needs to engineer new features from this existing data to improve model accuracy. Which of the following approaches to feature engineering best balances predictive power with the imperative to protect customer privacy and comply with data protection regulations? Option A. Directly incorporate raw, high-granularity transaction timestamps and precise geographical coordinates of all customer activities as individual features to capture the most detailed behavioral nuances. Option B. Develop complex, multi-layered features that require extensive computational resources and may lead to significant latency in model prediction, prioritizing theoretical completeness over practical application and privacy considerations. Option C. Engineer features that are highly specific combinations of individual purchase items and exact purchase times, aiming to create unique identifiers for each customer's transaction history. Option D. Create aggregated features representing spending patterns, e.g., average monthly spending in categories, frequency of transactions, and interaction terms between demographic attributes and aggregated financial behaviors, ensuring no direct individual identifiers are used in the final feature set. The correct answer is D. Create aggregated features representing spending patterns, e.g., average monthly spending in categories, frequency of transactions, and interaction terms between demographic attributes and aggregated financial behaviors, ensuring no direct individual identifiers are used in the final feature set. Explanation. Scenario analysis. This scenario presents a common challenge in professional data science, balancing the need for robust feature engineering to improve model performance with the imperative to maintain data privacy and comply with relevant regulations. The professional challenge lies in identifying and creating new, predictive features from sensitive data without inadvertently exposing or reconstructing personally identifiable information. PI. This requires a nuanced understanding of both data transformation techniques and the legal and ethical boundaries governing data usage. Careful judgment is needed to ensure that the pursuit of analytical insights does not compromise individual privacy rights. Correct approach analysis. The correct approach involves leveraging techniques that aggregate, anonymize, or transform features in a way that preserves their predictive power while obscuring direct links to individuals. For instance, creating ratios, interaction terms, or aggregated statistics, like average spending within a category, from existing transactional data can yield highly informative features. These transformations, when applied thoughtfully, can reduce the granularity of individual data points, making re-identification significantly more difficult. This aligns with the principles of data minimization and privacy by design, which are foundational to many data protection regulations. By focusing on derived, less sensitive features, the data scientist upholds ethical obligations and regulatory compliance, ensuring that the model's insights are derived responsibly. Incorrect approaches analysis. One incorrect approach would be to directly use raw, granular data fields that are highly specific to individuals, such as exact timestamps of every transaction or precise location data, as direct inputs for new features without any aggregation or anonymization. This poses a significant regulatory risk, as it increases the likelihood of re-identification, potentially violating data privacy laws that mandate the protection of PII. Another incorrect approach would be to engineer features that, while seemingly abstract, can be easily reverse-engineered to infer sensitive personal attributes. For example, creating a feature that represents a unique combination of purchase history and demographic information that, when analyzed in conjunction with other available data, could pinpoint an individual. This would also be a failure of ethical data handling and a potential breach of regulatory requirements. A third incorrect approach might involve creating features that are overly complex and computationally intensive to derive, leading to significant delays in model deployment and potentially impacting the real-time usability of the model, which, while not a direct privacy violation, represents poor professional practice in terms of efficiency and resource management. Professional reasoning. Professionals should approach feature engineering with a privacy-first mindset. The decision-making process should involve 1. Understanding the data's sensitivity and the regulatory landscape governing its use. 2. Prioritizing feature engineering techniques that inherently reduce identifiability, such as aggregation, generalization, or the creation of synthetic features that capture patterns without revealing individual details. 3. Conducting a thorough risk assessment for each engineered feature, evaluating its potential for re-identification or inference of sensitive attributes. 4. Documenting the feature engineering process meticulously, including the rationale for each transformation and the steps taken to mitigate privacy risks. 5. Iteratively testing and validating features not only for predictive power, but also for their privacy implications. Question 11. System analysis indicates that a new project requires the collection and processing of customer interaction data from various online channels to improve service personalization. The data scientist is tasked with designing the initial data pipeline. Which of the following approaches best mitigates potential risks associated with this data collection and processing? Option A. Implement a basic anonymization technique on the collected data without a formal assessment of its effectiveness or potential re-identification risks. Option B. Conduct a comprehensive risk assessment to identify potential privacy and security vulnerabilities before designing the data pipeline and implement controls based on the assessment findings. Option C. Focus solely on the technical requirements for ingesting and transforming the data, with the understanding that data governance and privacy concerns will be handled by a separate team. Option D. Proceed with collecting and processing all available customer interaction data to maximize the dataset for immediate analysis, assuming that any sensitive information can be addressed later. The correct answer is B. Conduct a comprehensive risk assessment to identify potential privacy and security vulnerabilities before designing the data pipeline, and implement controls based on the assessment findings. Explanation. This scenario presents a professional challenge due to the inherent tension between leveraging advanced data processing techniques for business insights and the imperative to protect sensitive personal data. The professional data scientist must navigate this by prioritizing data privacy and security throughout the data collection and processing lifecycle, aligning with the principles of responsible AI and data governance. The correct approach represents best professional practice because it proactively identifies and mitigates risks associated with data collection and processing. Conducting a thorough risk assessment, the data scientist ensures that potential privacy violations, data breaches, and noncompliance with relevant regulations, such as those governing data privacy and security in the U.S., like HIPAA for health data or CCPA for consumer data, depending on the specific context of the data being processed, are identified before they occur. This aligns with the principle of privacy by design and security by design, which are foundational to ethical and compliant data handling. It demonstrates a commitment to minimizing the attack surface and the potential for misuse of sensitive information, thereby building trust with data subjects and stakeholders. An incorrect approach that involves proceeding with data collection and processing without a formal risk assessment is professionally unacceptable. This failure constitutes a significant regulatory and ethical lapse. It demonstrates a disregard for data protection principles and potentially violates data privacy laws by exposing sensitive information to unnecessary risks. Such an approach could lead to severe consequences, including hefty fines, reputational damage, and legal liabilities. Another incorrect approach, focusing solely on the technical feasibility of processing data without considering its sensitivity or origin, is also professionally flawed. This oversight can lead to the inadvertent collection or processing of personally identifiable information, PI, or other sensitive data in ways that are not compliant with privacy regulations or ethical guidelines. It prioritizes immediate technical goals over long-term data stewardship and legal obligations. A third incorrect approach, assuming that anonymization is always sufficient without verifying its effectiveness or considering re-identification risks, is also problematic. While anonymization is a valuable technique, it is not foolproof. Inadequate anonymization can still leave data vulnerable to re-identification, especially when combined with other datasets. This failure to rigorously validate anonymization techniques can lead to unintentional data breaches and noncompliance with data protection laws that require robust de-identification measures. The professional decision-making process for similar situations should involve a structured risk management framework. This begins with clearly defining the scope of data collection and processing, identifying all potential data sources and types, and understanding the intended use of the data. Subsequently, a comprehensive risk assessment should be performed, considering threats to data confidentiality, integrity, and availability, as well as privacy risks. Mitigation strategies should be developed and implemented, followed by ongoing monitoring and review. This iterative process ensures that data is handled responsibly and in compliance with all applicable regulations and ethical standards. Question 12. Governance review demonstrates that a data science team is tasked with presenting findings on customer engagement metrics across different product lines over the past fiscal year. The team has collected data on customer interaction frequency, continuous, average session duration, continuous, and customer acquisition source, categorical. The primary objective is to highlight trends in engagement over time and compare the performance of different acquisition sources. Which combination of chart types would best facilitate clear and accurate communication of these findings to a non-technical executive team, adhering to principles of data integrity and effective reporting? Option A. Line charts for customer interaction frequency over time, and bar charts to compare average session duration by customer acquisition source. Option B. Box plots to compare interaction frequency across acquisition sources, and line charts to illustrate the distribution of session duration over time. Option C. Scatter plots to show the relationship between interaction frequency and session duration, and heat maps to visualize acquisition source performance. Option D. Histograms to display the distribution of interaction frequency and session duration, and geographic maps to represent acquisition source locations. Correct answer is A. Line charts for customer interaction frequency over time, and bar charts to compare average session duration by customer acquisition source. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects, effectively communicating complex findings to diverse stakeholders with varying levels of technical expertise. The professional challenge lies in selecting visualization types that accurately represent the data, are easily interpretable, and adhere to best practices for data storytelling, all while ensuring compliance with data governance policies that may dictate clarity and auditability of reporting. The need for careful judgment arises from the potential for misinterpretation or misleading conclusions if inappropriate charts are used, impacting business decisions and trust in the data. Correct approach analysis. The correct approach involves selecting chart types that are best suited for the specific data relationships and the intended audience. For instance, a histogram is ideal for showing the distribution of a single continuous variable, a scatter plot for examining the relationship between two continuous variables, a bar chart for comparing discrete categories, and a line chart for illustrating trends over time. Heat maps are effective for visualizing matrix data or correlations, while geographic maps are essential for spatial data. Box plots are valuable for comparing distributions across different groups. This approach represents best professional practice because it prioritizes clarity, accuracy, and interpretability, which are fundamental to ethical data science and effective communication. Adhering to these visualization principles ensures that insights are conveyed truthfully and that stakeholders can make informed decisions based on a clear understanding of the data, aligning with principles of transparency and accountability often embedded in data governance frameworks. Incorrect approaches analysis. Using a histogram to compare discrete categories would be a regulatory and ethical failure because it misrepresents the data type, leading to an inaccurate visual impression and potentially flawed conclusions. Similarly, employing a scatter plot to show a trend over time would be inappropriate. A line chart is designed for this purpose, and a scatter plot would obscure the temporal progression. Presenting a heat map to show the distribution of a single continuous variable is inefficient and confusing, failing to leverage the heat map's strength in representing relationships within matrices. Using a bar chart to display the relationship between two continuous variables would also be a misapplication, as it would discreditize continuous data and obscure nuanced correlations. These misapplications violate ethical principles of data integrity and accuracy, potentially leading to misleading reports and undermining stakeholder trust, which can have regulatory implications if data-driven decisions are subsequently challenged. Professional reasoning. Professionals should adopt a systematic decision-making process when selecting chart types. This involves first understanding the nature of the data, categorical, continuous, temporal, spatial, the specific question being asked or the insight to be conveyed, and the characteristics of the intended audience. A review of established data visualization best practices and guidelines, often incorporated into organizational data governance policies, is crucial. When in doubt, it is best to err on the side of clarity and simplicity, choosing a chart type that is widely understood and accurately represents the data. Documenting the rationale for chart selection can also be a valuable part of the professional reasoning process, especially in regulated environments. Question 13. Operational review demonstrates that a financial services firm is experiencing significant volatility in its daily trading volumes. The data science team is tasked with developing a robust forecasting model to predict these volumes for resource allocation and risk management purposes. The firm operates under U.S. regulatory frameworks, requiring high accuracy and auditability of financial predictions. The team has access to historical daily trading volume data spanning several years. Which of the following approaches best aligns with regulatory expectations for developing a reliable and auditable time series forecast for trading volumes? Option A. Directly apply a deep learning forecasting model, such as an LSTM, to the raw historical trading volume data, optimizing for the lowest root mean squared error, RMSE, on a held-out test set without explicit stationarity testing or autocorrelation analysis. Option B. Employ a seasonal decomposition of the time series to isolate trend, seasonality, and residual components, and then forecast each component independently using separate regression models, without explicitly addressing the stationarity of the residual component before forecasting. Option C. Use a simple moving average SMA of the last 30 days of trading volumes as the sole forecasting method, assuming that recent trends are the most indicative of future volumes, and do not perform any statistical tests or model validation. Option D. Conduct a thorough analysis of the time series data, including statistical tests for stationarity, e.g., augmented Dickey-Fuller test, differencing the series if non-stationary, and then analyzing the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots to inform the selection and order of an ARIMA model, followed by rigorous model diagnostics and validation. The correct answer is A. Directly apply a deep learning forecasting model, such as an LSTM, to the raw historical trading volume data, optimizing for the lowest root mean squared error, RMSE, on a held-out test set without explicit stationarity testing or autocorrelation analysis. Explanation. This scenario presents a common challenge in time series analysis within a regulated environment, ensuring that forecasting models are not only accurate but also interpretable and compliant with industry standards for financial reporting and risk management. The professional challenge lies in balancing the predictive power of complex models with the need for transparency and auditability, especially when these forecasts influence critical business decisions or regulatory disclosures. The specific jurisdiction for this exam is assumed to be the United States, adhering to SEC, Securities and Exchange Commission, and potentially FINRA, Financial Industry Regulatory Authority, guidelines were applicable to financial data. The correct approach involves a methodical process of understanding and addressing stationarity, which is fundamental to reliable time series forecasting. Stationarity implies that the statistical properties of the time series, mean, variance, autocorrelation, do not change over time. Non-stationary data can lead to spurious correlations and unreliable forecasts. Techniques like differencing or transformations are used to achieve stationarity. Autocorrelation analysis, ACF and PACF plots, is crucial for identifying the underlying structure of the stationary series, guiding the selection of appropriate ARIMA, autoregressive integrated moving average, model orders. Moving averages smooth out short-term fluctuations and highlight longer-term trends, aiding in understanding the series behavior. ARIMA models built upon these concepts provide a robust framework for modeling and forecasting time series data. The choice of an appropriate ARIMA model, validated through diagnostic checks, e.g., residual analysis, and its subsequent application for forecasting, represents best professional practice because it adheres to principles of sound statistical modeling and data integrity, which are implicitly required by regulatory bodies like the SEC to ensure the accuracy and reliability of financial information. This approach promotes transparency and allows for clear justification of forecasting methodologies, crucial for audits and regulatory scrutiny. An incorrect approach would be to directly apply a complex, black box forecasting model without first assessing or addressing stationarity. This is a regulatory and ethical failure because it risks generating forecasts based on spurious relationships, leading to potentially misleading financial projections or risk assessments. Such a practice violates the implicit requirement for due diligence and sound methodology in financial forecasting, which could be subject to SEC review for accuracy and completeness. Another incorrect approach would be to rely solely on visual inspection of raw time series plots without formal statistical tests for stationarity or autocorrelation analysis. While visual inspection can be a starting point, it is insufficient for rigorous analysis. This represents a failure in professional due diligence, as it bypasses established statistical methods necessary for model selection and validation. Regulatory bodies expect a data-driven and statistically sound approach, not one based on subjective interpretation alone. A third incorrect approach would be to select an ARIMA model based purely on achieving the lowest in-sample error metric, without considering model interpretability or the underlying statistical assumptions. While minimizing error is important, it should not come at the expense of understanding the model's behavior or its suitability for the data. This can lead to overfitting or models that do not generalize well, potentially resulting in inaccurate future predictions. This is a failure in professional judgment, as it prioritizes a single metric over a holistic understanding of model performance and reliability, which is critical for regulatory compliance and trustworthy forecasting. The professional decision-making process for similar situations should involve a structured approach. 1. Understand the business context and the purpose of the forecast. 2. Thoroughly explore the data, including visualization and descriptive statistics. 3. Rigorously assess stationarity using statistical tests and transformations if necessary. 4. Analyze autocorrelation to understand the temporal dependencies, 5. Select candidate ARIMA models based on statistical insights and domain knowledge. 6. Validate chosen models through residual analysis and other diagnostic checks. 7. Evaluate forecast performance using appropriate metrics and consider forecast uncertainty. 8. Document all steps, assumptions, and justifications for auditability and transparency. Question 14. Process analysis reveals that a new AI-driven customer personalization engine is critical for maintaining a competitive edge. The engineering team is eager to deploy the engine rapidly using newly acquired, high-volume customer interaction data. As the lead data scientist, you are tasked with ensuring the engine is both effective and compliant. Which of the following approaches best balances the need for rapid deployment with robust data governance? Option A. Implement data security measures only after the AI engine is fully operational and has demonstrated initial success in the market. Option B. Implement comprehensive data quality checks, establish clear data lineage tracking, develop a data catalog, and enforce strict data security protocols concurrently with the AI model development lifecycle, prioritizing these foundational elements before full-scale deployment. Option C. Deploy the AI model immediately to capture market advantage and address data quality, lineage, cataloging, and security concerns in subsequent iterative updates after the initial launch. Option D. Focus solely on model performance metrics during development and deployment, deferring all data governance activities to a separate post-deployment audit. The correct answer is B. Implement comprehensive data quality checks, establish clear data lineage tracking, develop a data catalog, and enforce strict data security protocols concurrently with the AI model development lifecycle, prioritizing these foundational elements before full-scale deployment. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects, balancing the need for rapid deployment of AI-driven insights with robust data governance practices. The pressure to deliver a competitive advantage by leveraging new customer data creates a tension with the imperative to ensure data quality, lineage, security, and compliance. A data scientist must navigate this by understanding that while speed is important, compromising on governance can lead to significant risks, including regulatory penalties, reputational damage, and flawed decision-making based on unreliable data. The challenge lies in integrating governance seamlessly into the development lifecycle, rather than treating it as an afterthought. Correct approach analysis. The correct approach emphasizes establishing a comprehensive data governance framework before or concurrently with the AI model development. This involves defining clear data quality standards, implementing robust data lineage tracking mechanisms to understand data transformations, creating a centralized data catalog for discoverability and understanding, and enforcing stringent data security protocols. This proactive approach aligns with the principles of responsible AI and data management, ensuring that the AI models are built on a foundation of trustworthy and secure data. From a regulatory perspective, this aligns with the spirit of data protection laws, e.g., GDPR in the EU, CCPA in California, or similar frameworks relevant to the exam's jurisdiction, which mandate data accuracy, security, and accountability. By embedding governance early, the data scientist demonstrates a commitment to ethical data handling and mitigates risks associated with non-compliance and poor data integrity. Incorrect approaches analysis. An approach that prioritizes immediate model deployment without establishing data quality checks or lineage tracking is fundamentally flawed. This creates a significant risk of building models on inaccurate or incomplete data, leading to biased or erroneous predictions. Ethically, it fails to uphold the principle of data integrity. From a regulatory standpoint, it can violate data accuracy requirements and make it impossible to demonstrate compliance or respond to data subject requests effectively. Another incorrect approach is to implement data security measures only after the model is deployed. This leaves sensitive customer data vulnerable during the development and testing phases, increasing the risk of data breaches. This is a direct violation of data security mandates and can result in severe legal and financial penalties, as well as a loss of customer trust. Finally, neglecting to create a data catalog or document data lineage means that the origin, transformations, and meaning of the data used in the AI model remain obscure. This lack of transparency hinders auditing, debugging, and future model improvements. It also makes it difficult to comply with regulations that require clear understanding and documentation of data processing activities. Professional reasoning. Professionals should adopt a governance by design mindset. This involves integrating data governance principles into every stage of the data science lifecycle, from data acquisition and preparation to model development, deployment, and monitoring. When faced with pressure to accelerate deployment, professionals should advocate for a phased approach where essential governance elements are prioritized for initial deployment, with a clear roadmap for implementing more comprehensive controls. This requires effective communication with stakeholders about the risks of neglecting governance and the long-term benefits of a well-governed data ecosystem. The decision-making process should always weigh the potential business benefits against the regulatory, ethical, and operational risks. Question 15. Process analysis reveals that a dataset of customer transaction values exhibits a right-skewed distribution, with a few very large transactions significantly higher than the majority of smaller ones. When preparing a summary report for business stakeholders to understand the typical transaction amount, which descriptive statistic would best represent the central tendency of this data, and why? Option A. The median, as it is unaffected by extreme values and provides a true middle point of the data. Option B. The standard deviation, as it quantifies the variability around the average transaction value. Option C. The mean, as it considers every data point and is a common measure of central tendency. Option D. The range, as it indicates the spread of the data and highlights the impact of large transactions. The correct answer is A. The median, as it is unaffected by extreme values and provides a true middle point of the data. Explanation. This scenario is professionally challenging because it requires a data scientist to select the most appropriate descriptive statistic to represent a dataset, considering the potential for outliers and the need for clear, unbiased communication of findings. The choice of statistic directly impacts how stakeholders understand the data, and an inappropriate choice can lead to misinterpretations and flawed business decisions. Regulatory compliance in data science, particularly in a professional context like the Google Cloud Professional Data Scientist exam, emphasizes the ethical responsibility to present data accurately and transparently. This involves understanding the properties of different statistical measures and their suitability for various data characteristics. The correct approach represents best professional practice because it prioritizes a measure of central tendency that is robust to extreme values. The median is the middle value in a sorted dataset, and it is not unduly influenced by outliers. This aligns with the ethical imperative to provide a representative summary of the data, especially when the distribution might be skewed. In a professional setting, especially when reporting to non-technical stakeholders, using a robust measure like the median ensures that the summary statistic accurately reflects the typical value without being distorted by a few unusual data points. This promotes trust and informed decision-making, which are critical in any regulated industry or professional environment. An incorrect approach that uses the mean without considering the data's distribution or potential outliers is professionally unacceptable. The mean is sensitive to extreme values. A single very high or very low data point can significantly skew the mean, making it a poor representation of the central tendency of the majority of the data. This can lead to misleading conclusions and potentially unethical reporting if the skewness is not acknowledged or understood. For example, if reporting average salaries, a few exceptionally high salaries could inflate the mean, making it appear that the typical employee earns more than they actually do. This misrepresentation can have ethical implications, particularly if it affects compensation discussions or resource allocation. Another incorrect approach that focuses solely on measures of dispersion without adequately addressing central tendency fails to provide a complete picture. While dispersion measures like standard deviation or range are important for understanding variability, they do not, by themselves, tell us where the center of the data lies. A professional decision-making process should involve a holistic understanding of the data. When faced with a choice of descriptive statistics, a data scientist should first consider the nature of the data, e.g., presence of outliers, distribution shape, and the purpose of the analysis. Then, they should select the statistic that best summarizes the data's central tendency in a way that is both accurate and interpretable for the intended audience, while also considering relevant dispersion measures to provide context. This iterative process of understanding, selecting, and contextualizing ensures that the data is presented responsibly and ethically. Question 16. The control framework reveals that a new predictive model for customer churn requires integrating data from multiple sources. The data scientist has identified potential sources including a public API for demographic data, a company's internal SQL database containing transaction history, a third-party web service providing market trends, and publicly accessible web pages with competitor pricing. To ensure compliance and ethical data handling, which approach to data sourcing is most appropriate? Option A. Proceed with extracting data from all identified sources immediately to gather the most comprehensive dataset for initial model exploration, addressing compliance concerns later if they arise. Option B. Directly scrape all publicly available web pages, including competitor pricing and market trend data, and ingest data from the public API without verifying its usage policies, assuming that public availability implies unrestricted access. Option C. Prioritize integrating data from the public API and the internal SQL database, while thoroughly reviewing the terms of service for the third-party web service and the robots. TXT file and terms of use for the competitor pricing web pages before attempting any data extraction. Option D. Focus solely on the internal SQL database and the competitor pricing web pages, as these are the most readily accessible and likely to contain the necessary information, disregarding external APIs and third-party services due to potential complexity. The correct answer is C. Prioritize integrating data from the public API and the internal SQL database, while thoroughly reviewing the terms of service for the third-party web service and the robots. TXT file and terms of use for the competitor pricing web pages before attempting any data extraction. Explanation. This scenario is professionally challenging because it requires balancing the need for comprehensive data for advanced analytics with the strict regulatory requirements governing data access and usage within a cloud environment. The data scientist must ensure that all data sources are not only technically accessible, but also legally and ethically permissible for the intended analysis, adhering to the specific data governance policies mandated by the exam's jurisdiction. The correct approach represents best professional practice because it prioritizes a thorough understanding and validation of data source compliance before ingestion. This involves verifying that APIs are used within their terms of service, web scraping adheres to robots, TXT and ethical considerations, databases are accessed with appropriate permissions, and cloud storage buckets are configured with granular access controls aligned with data classification policies. This proactive compliance ensures that the data used for analysis is obtained and handled legally, ethically, and securely, minimizing the risk of regulatory violations and data breaches. An incorrect approach that involves directly scraping a public website without verifying its terms of service or robots. TXT file poses a significant regulatory and ethical failure. This could violate intellectual property rights, terms of use agreements, and potentially lead to legal repercussions for unauthorized data collection. Another incorrect approach, such as accessing a production database without explicit authorization or understanding of its data sensitivity, represents a severe breach of data security and privacy regulations, potentially leading to unauthorized access to sensitive information and significant compliance penalties. Finally, ingesting data from an unsecured cloud storage bucket without proper access controls or data anonymization, if applicable, would violate data protection laws and ethical standards, exposing sensitive information and risking reputational damage. Professionals should employ a decision-making framework that begins with a clear understanding of the project's analytical objectives. This is followed by a comprehensive inventory of potential data sources, a rigorous assessment of each source's compliance with relevant regulations and internal policies, and the implementation of secure and authorized data ingestion methods. Documentation of data lineage, access controls, and compliance checks is crucial throughout the process. Question 17. Stakeholder feedback indicates a desire to leverage customer purchase history to personalize marketing campaigns, but there are concerns about data privacy and the potential for discriminatory targeting. As a data scientist, which approach best balances these competing demands while adhering to responsible data practices? Option A. Conduct a thorough data governance review, define clear ethical guidelines for data usage, establish anonymization protocols for sensitive data, and develop a phased rollout plan for the personalization initiative, starting with a limited, controlled pilot. Option B. Immediately begin building predictive models based on available data, assuming that any insights generated will be beneficial and can be refined later if issues arise. Option C. Develop a sophisticated recommendation engine using advanced machine learning techniques, prioritizing predictive accuracy and deploying it rapidly to capture market opportunities. Option D. Focus solely on identifying the most profitable customer segments based on historical data, without explicitly considering the ethical implications of how these segments are defined or targeted. The correct answer is C. Develop a sophisticated recommendation engine using advanced machine learning techniques, prioritizing predictive accuracy and deploying it rapidly to capture market opportunities. Explanation. This scenario is professionally challenging because it requires balancing competing stakeholder interests and ensuring that data science initiatives align with both business objectives and regulatory compliance. The data scientist must navigate the complexities of data privacy, security, and ethical considerations inherent in using sensitive customer data, all while aiming to deliver actionable insights. Careful judgment is required to select a decision-making framework that is robust, transparent, and defensible. The correct approach represents best professional practice because it prioritizes a structured, iterative, and collaborative process. By involving stakeholders early and often, defining clear objectives, and establishing measurable success criteria, the data scientist ensures alignment and manages expectations. This approach fosters trust and accountability, crucial for ethical data handling and regulatory adherence. It allows for continuous evaluation against established metrics, enabling timely adjustments and mitigating risks associated with misinterpretation or misuse of data. This aligns with the principles of responsible AI and data governance, which are increasingly mandated by regulatory bodies to protect individuals and ensure fair outcomes. An incorrect approach that focuses solely on technical feasibility without considering stakeholder input or ethical implications fails to address the broader impact of the data science project. This can lead to solutions that are technically sound but do not meet business needs or, worse, violate privacy regulations by mishandling sensitive data. Another incorrect approach that prioritizes speed over thoroughness risks introducing biases, errors, or security vulnerabilities into the models, which can have significant financial and reputational consequences and potentially lead to regulatory penalties for noncompliance with data protection laws. A third incorrect approach that relies on anecdotal evidence or gut feeling rather than data-driven validation undermines the credibility of the data science function and can lead to flawed decision-making, potentially resulting in discriminatory outcomes or inefficient resource allocation, which can also have regulatory implications if fairness is compromised. Professionals should employ a decision-making framework that begins with a clear problem definition, followed by data exploration and understanding, model development and validation, and finally, deployment and monitoring. Throughout this process, continuous stakeholder engagement and ethical review are paramount. This iterative approach, grounded in a clear understanding of the problem, data, and potential impacts, ensures that data science solutions are not only technically robust, but also ethically sound, compliant with regulations, and aligned with strategic business goals. Question 18. Market research demonstrates that a significant portion of users are abandoning the checkout process on an e-commerce platform. A data scientist is tasked with building a predictive model to identify users at high risk of abandonment so that targeted interventions can be applied. The available data includes user demographics, browsing history, cart contents, and past purchase behavior. The data scientist has identified several potential features that could be highly predictive, but also suspects that some demographic features might inadvertently introduce bias into the model, potentially leading to unfair targeting of certain user groups. Which of the following approaches best aligns with responsible data science practices and regulatory expectations for developing such a predictive model? Option A. Focus on building a model that uses only non-demographic features, even if it results in a less accurate prediction of abandonment, to proactively avoid any potential for bias related to user characteristics. Option B. Immediately deploy a simple rule-based system that flags users who have more than 3 items in their cart and have not viewed a product in the last 10 minutes, as this is a common pattern observed in past abandonment cases, and then refine the system based on intervention success rates. Option C. Prioritize the development of a highly accurate predictive model using all available features, including demographic data, and then address any identified biases post-deployment through a /B testing of intervention strategies. Option D. Conduct a thorough exploratory data analysis to understand the distribution and potential impact of demographic features on abandonment. Implement bias detection techniques and mitigation strategies during model development, and document all steps taken to ensure fairness and transparency before deploying the model for targeted interventions. The correct answer is C. Prioritize the development of a highly accurate predictive model using all available features, including demographic data, and then address any identified biases post-deployment through a /B testing of intervention strategies. Explanation: this scenario is professionally challenging because it requires balancing the immediate business need for actionable insights with the ethical and regulatory obligations surrounding data privacy and responsible AI development. The data scientist must navigate potential biases in the data and model, ensuring that the insights derived are fair, transparent, and do not lead to discriminatory outcomes, which is a core tenet of responsible data science practice and aligns with general principles of data protection and ethical AI. The correct approach represents best professional practice because it prioritizes a thorough understanding of the data and potential biases before deploying a model for stakeholder consumption. This involves rigorous exploratory data analysis, bias detection, and mitigation strategies. Such an approach ensures that the insights provided to stakeholders are reliable, fair, and compliant with ethical guidelines for AI development and deployment, which are increasingly being codified in regulations and industry best practices. It fosters trust with stakeholders by demonstrating a commitment to data integrity and responsible innovation. An incorrect approach that focuses solely on delivering a model quickly, without addressing potential biases, is professionally unacceptable. This failure constitutes a significant ethical lapse and a potential regulatory violation. Specifically, it risks perpetuating or amplifying existing societal biases present in the data, leading to unfair or discriminatory outcomes for certain user groups. This can result in reputational damage, loss of customer trust, and legal repercussions, especially as data protection and AI ethics regulations become more stringent. Another incorrect approach that involves using sensitive personal data without proper anonymization or consent, even if for a seemingly beneficial purpose, directly violates data privacy principles and regulations, leading to severe legal and ethical consequences. Professionals should employ a decision-making framework that begins with clearly defining the business problem and understanding the data's context. This is followed by a comprehensive data exploration phase, including bias assessment. Mitigation strategies should be implemented and validated. Model development should proceed with fairness and transparency as key considerations. Finally, the deployment and ongoing monitoring of the model must include mechanisms for detecting and addressing drift or emergent biases, ensuring continuous ethical compliance and responsible AI governance. Question 19. Market research demonstrates that various data visualization tools offer distinct capabilities for presenting insights derived from Google Cloud data. A data scientist is tasked with creating a dashboard to monitor key performance indicators for a marketing campaign. The primary goals are to provide actionable insights to the marketing team, ensure the visualizations are easily understandable, and maintain compliance with internal data governance policies. Which approach best addresses these requirements? Option A. Opt for a tool that requires minimal setup and learning curve, even if it has limited customization or integration options, to quickly generate a basic set of charts that can be shared with the marketing team. Option B. Choose the tool that is most widely used in the industry, regardless of its specific integration capabilities with Google Cloud or its data governance features, and focus on replicating popular dashboard designs found online. Option C. Select a tool that offers a wide range of advanced chart types and customization options, allowing for highly detailed and visually striking presentations, and then proceed to build the dashboard with the most aesthetically pleasing designs. Option D. Prioritize a tool that integrates seamlessly with Google Cloud services, offers robust data governance features, and enables the creation of clear, intuitive visualizations that directly address the marketing team's key performance indicators, while also considering the ease of sharing and collaboration. The correct answer is C. Select a tool that offers a wide range of advanced chart types and customization options, allowing for highly detailed and visually striking presentations, and then proceed to build the dashboard with the most aesthetically pleasing designs. Explanation: this scenario presents a professional challenge due to the need to balance the technical capabilities of various data visualization tools with the specific regulatory and compliance requirements of the Google Cloud Professional Data Scientist exam's implied jurisdiction, which, for the purpose of this exam, we assume aligns with general U.S. data privacy and security principles, such as those found in HIPAA or GDPR-like frameworks, if sensitive data were involved, or general best practices for data handling and reporting if not. The challenge lies in selecting a tool that not only effectively communicates insights, but also adheres to any implicit or explicit guidelines regarding data handling, access control, and the potential for misinterpretation or misuse of visualized data. Careful judgment is required to ensure the chosen tool and its application meet both technical and governance standards. The correct approach represents best professional practice because it prioritizes a comprehensive evaluation of visualization tools based on their suitability for the specific task, considering factors like ease of use, integration with Google Cloud services, and the ability to generate clear, accurate, and defensible visualizations. It also implicitly acknowledges the need to understand the underlying data and the audience's needs, which are foundational to responsible data science. This approach aligns with ethical data science principles by aiming for clarity and accuracy, thereby minimizing the risk of misinterpretation or the generation of misleading insights. From a regulatory perspective, choosing a tool that facilitates clear and audible reporting is crucial, especially if the data has compliance implications. An incorrect approach that focuses solely on the aesthetic appeal of visualizations, without considering their accuracy or the underlying data's integrity, would be professionally unacceptable. This could lead to the creation of misleading dashboards that, while visually pleasing, misrepresent findings and could result in poor business decisions or, in regulated industries, compliance violations. Another incorrect approach that relies on a tool with limited data governance features or poor integration with secure cloud environments could expose sensitive data or create unmanageable access logs, posing significant security and privacy risks, which are often subject to strict regulatory oversight. A third incorrect approach that ignores the audience's technical proficiency and presents overly complex visualizations could lead to misinterpretation, undermining the purpose of the analysis and potentially leading to negative business outcomes or compliance issues if the insights are misunderstood. The professional reasoning process should involve a thorough understanding of the project's objectives, the nature of the data, the intended audience, and any relevant regulatory or compliance frameworks. When selecting visualization tools, professionals should consider their capabilities in terms of data connection, transformation, visualization types, interactivity, sharing, and importantly, security and governance features. A structured evaluation process, including pilot testing and stakeholder feedback, is essential to ensure the chosen tool effectively supports accurate, ethical, and compliant data communication. Question 20. Strategic planning requires a data scientist to design a secure and compliant data access framework for sensitive customer information stored on Google Cloud. Considering the organization's commitment to data privacy regulations, which approach best leverages discrete mathematical principles to ensure that data is only accessible to authorized personnel and systems, while minimizing the risk of unauthorized disclosure. Option A. Define data access policies by creating distinct sets of data based on broad categories, e.g., customer data, transaction data, and assigning users to these sets without explicitly modeling the interdependencies between data elements or user roles. Option B. Model the data as a directed graph where nodes represent individual data points and edges represent potential access pathways. User permissions are then defined as specific traversal rights within this graph, ensuring that access is granted only through explicitly permitted paths, and data is treated as belonging to specific, well-defined sets based on its attributes and sensitivity. Option C. Focus solely on the volume of data being accessed, creating access tiers based on data size rather than its content or the relationships between different data elements and user responsibilities. Option D. Implement a single overarching access control list, ACL, for all customer data, granting broad read and write permissions to all data science team members to facilitate rapid model development. The correct answer is A. Define data access policies by creating distinct sets of data based on broad categories, e.g., customer data, transaction data, and assigning users to these sets without explicitly modeling the interdependencies between data elements or user roles. Explanation. Scenario analysis. This scenario is professionally challenging because it requires balancing the need for efficient data processing and model deployment on Google Cloud with the strict requirements of data governance and privacy regulations. The data scientist must understand how discrete mathematical concepts, specifically set theory and graph theory, underpin the organization of data and access controls, and how these relate to compliance. The challenge lies in translating abstract mathematical principles into concrete, compliant operational decisions within a cloud environment, ensuring that data access and processing adhere to legal and ethical standards without hindering innovation. Correct approach analysis. The correct approach involves leveraging an understanding of set theory to define granular data access policies and graph theory to model relationships between data entities and user roles. This allows for the implementation of a robust access control mechanism that aligns with the principle of least privilege, a cornerstone of data protection regulations. By treating data assets as elements within sets and user permissions as relationships within a graph, the data scientist can systematically identify and restrict access to sensitive information, thereby minimizing the risk of unauthorized disclosure or misuse. This approach directly supports compliance with data privacy laws by ensuring that only authorized individuals or systems can access specific data subsets, and that the flow of data is auditable and controlled. This aligns with the spirit and letter of regulations that mandate data minimization and purpose limitation. Incorrect approaches analysis. One incorrect approach is to implement broad, permissive access controls based on a simplistic understanding of data grouping, neglecting the detailed relationships and potential pathways for data exfiltration. This fails to adhere to the principle of least privilege and creates significant regulatory risk, as it can lead to unauthorized access to sensitive data, violating data privacy laws. Another incorrect approach is to over-engineer access controls by creating overly complex and restrictive policies that hinder legitimate data analysis and collaboration. While seemingly cautious, this can lead to operational inefficiencies and may not be directly mandated by regulations, potentially creating unnecessary barriers to innovation without a clear compliance benefit. Furthermore, ignoring the underlying graph structures of data relationships and user permissions can lead to blind spots in security, where seemingly unrelated data points can be linked through indirect pathways, leading to unintended data exposure and non-compliance with data governance frameworks. Professional reasoning. Professionals should adopt a systematic approach that begins with a thorough understanding of the data's structure and relationships, informed by discrete mathematics. This understanding should then be mapped against regulatory requirements for data access, processing, and privacy. The process involves defining clear sets of data and user roles, and modeling the relationships between them using graph theory to ensure that access controls are both comprehensive and efficient. Regular auditing and review of these structures and policies are crucial to maintain compliance and adapt to evolving threats and regulations. This iterative process of modeling, implementing, and auditing ensures that data science practices remain compliant and ethically sound.